Hello there and welcome to this video which will take you through the contact process, the process that's used industrially for manufacturing sulfur dioxide. This is primarily aimed for Gcse, Cambridge chemistry students, but this is applicable to any Gcse specification that requires you to study the contact process and the manufacture of sulfuric acid. So these are the four learning objectives that I hope to be covering in today's video. So my general tip for anything that you see in a specification that says state is try and put it on a flashcard because they will want you to write it down as is, word for word, letter for letter, subscript for subscript. So the three things that you will need to be able to memorize and recall in the exam is being able to give the simple equation for the conversion of sulfur dioxide to sulfur trioxide in the contact process. That's this equation over here. Also, state the sources of sulfur dioxide, which is burning sulfur or roasting sulfide ores. If you roast the sulfide ores, such as iron sulfide, the sulfur part of the sulfide ore will combine with oxygen in the air to give you sulfur dioxide. So that process is something that takes place at high temperature. So it is called roasting. But if you actually have a source of sulfur, typically found in underground sources, near volcanoes as well, but there are underground sources, and you can also get the sulfur from flue gas desulfurization of natural gas as well. So if you get that sulfur and you control the burning of that sulfur in oxygen, which is obviously found in air, so if you just burn the sulfur in air, you actually also get the sulfur dioxide that you require for the contact processes. The typical conditions for the conversion within the industry is 450 degrees Celsius, 2 atmospheres, and a vanadium 5 oxide catalyst. So the video that I'm about to quote to you to have a look at in between different parts of my video quotes 440 degrees Celsius. However, Cambridge specify 450 degrees Celsius, so I would recommend that you recall 450. The reality of the situation is there isn't really too much difference between 440 and 450. It's neither here or there. 2 atmospheres is chosen, even though you may think you've got larger volumes on the left-hand side, larger gas volumes on the left and on the right. So if you were to place this under high pressure, you would actually drive the equilibrium over to the right-hand side because your forward reactions are actually taking place at a higher rate than the reverse reactions. The reality of the situation is this is quite an efficient process. So 2 atmospheres is generally chosen. And it also links to safety considerations as well. There's no need to go beyond 2 atmospheres because of safety. Larger pressures than 2 atmospheres would actually require more sturdy pipes, more sturdy tanks. You just generally with the contact process, it happens really, really well. So you want to try and dumb it down, so to speak. You just want to try and control it, and there are some safety features and considerations that we will look into that help us control, particularly the exothermicity of this reaction. It does release a lot of heat, and we'll also try and see how that heat can be used to make the process a little more profitable. So a quick rundown on sulfur dioxide. It is a gas. It forms when sulfur burns in air. It's colorless and heavier than air, with a strong choking smell, and like most non-metal oxides, it's acidic, so it will dissolve in water. The sulfurous acid that forms when sulfur dioxide dissolves in water actually breaks down easily again to sulfur dioxide and water. So not very stable. We want to try and get something a little more stable. We find that sulfuric acid, H2SO4, is more stable for industrial uses and purposes. It does actually act as a bleach, so we use it to bleach wood, wool, silk, and wood pulp for making paper. Because it actually removes the color from colored compounds. It's a really good reducing agent. And it kills bacteria, so it's used as a sterilizing agent in making soft drinks and jam, and in drying fruit. You'll find that sometimes on your dried fruit, your rehydrated dried apricots, for example, on the right-hand side of your screen, you can see that there's an allergy advice, contains sulfur dioxide. Sometimes it actually has the preservative stated as sulfur dioxide because it stops the growth of these bacteria and molds, and it preserves the food that you adding them. A QR code, and I will ask you, I'll encourage you to go into that QR code and have a look at the 5-minute presentation that the Royal Society of Chemistry have produced for the actual industry, because it actually shows you about the steps that are taken. It shows you some real life visitations of the sulfuric acid industry. Go and check it out. It's really cool video. I have summarized the video in this presentation, but it's an extra 5.5 minutes, and it's actually a really good resource. So I strongly recommend that you watch that, and you can pause this video and you can go scan it and watch that video, and it will take you through it. It will keep you really interested in it as well. So here's a quick summary of the industry that you would have seen in your video. So air containing oxygen is one of the raw materials that's used for the industry. You've got sulfur, and later on down the line and along the process at various steps, you actually need water. But you do need water at some stage to help dilute your super hyper concentrated version of sulfuric acid. So you start off by roasting your sulfur dioxide along with oxygen. So you actually have sulfur that goes in the first step. You heat it to a high temperature with air, and you form sulfur dioxide, and then you continually heat that up to 450 degrees Celsius in the presence of more air, which contains oxygen, and you just run it through your converter. This contains 4 beds of your vanadium 5 oxide catalyst. You run it under a pressure of 2 atmospheres. Along the way, what you do is you take away you remove the heat that's generated because of the exothermicity of these steps. You remove it by passing it on the inside of coils of water. Those water coils contain water, and that water will turn into steam, and the steam can then be used to generate electricity. So that helps you with the economic side. And we tend to want to remove the heat because we want to try and look at it from a position of safety consideration as well. And if it's too hot, that can become quite dangerous. So as we run our gas mixture past these beds of catalysts, more and more of the sulfur dioxide is converted to sulfur trioxide, and between the 3rd and the 4th bed, your sulfur trioxide is then run past some sulfuric acid. And that's the sulfuric acid that's already been made within the factory now. What then happens is the sulfur trioxide at that stage dissolves in the sulfuric acid. You can imagine it like carbonated fizzy water. So fizzy water contains carbon dioxide, and it's dissolved in water, and when you release the pressure, the fizz comes out. You've got the carbon dioxide that bubbles out. So in a similar situation, you've actually got sulfur trioxide dissolving in this 98.5% sulfuric acid. So your concentration actually then steps up to around about 99%. It's a super concentrated version called oleum. And what you then do is you pass this super concentrated version of sulfuric acid through a diluter, and at that stage you slowly add water. And when you slowly add water, there's heat generated, and again you can remove that heat through the water coils that can then turn the the water within the coils to steam to sell off for electricity, keeping it positive in terms of economics. And when you dilute your sulfuric acid, at 99%, it goes back to 98.5% sulfuric acid. And any extra that you've formed can then be separated off for sale. Some students actually find that step a little bit confusing. So you can imagine that if you start off with 1 bucket of sulfuric acid, you then bubble this sulfur trioxide through, and you dissolve the sulfur trioxide into this 1 bucket of sulfuric acid. So you get your oleum, you get your 99% sulfuric acid, hyper, super concentrated version. You then slowly add water to that bucket. You turn that bucket into 2 buckets of sulfuric acid. You return back to your original concentration. 1 bucket you recycle into the industrial process, and the other bucket you can actually then separate off for sale. So that, I hope, will be a little clearer to you. So in the converter, what actually happens is you get your SO2 plus O2 mix, and it passes through the first bed of vanadium 5 oxide, and as a result, 63% of the sulfur dioxide is converted. The hot gases, because the cold they're relatively cool. The hot gases that pass from that conversion pass through a separate chamber, and then they are cooled down. So you actually pass water on the outside of this. The water turns to steam. The steam then helps with the economics and safety. So the cooled gases are then passed through a second bed of vanadium 5 oxide. Your conversion then goes to 88%. The hot gases pass out, they're cooled again. Then they pass through another bed of vanadium 5 oxide. Now your conversion rate is up to 95%. The warm gases pass out at this stage into an absorber. The absorber starts to absorb the sulfur trioxide that's in that mixture. So the sulfur trioxide dissolves in actually dissolves in sulfuric acid. So at this stage, your 95% comes through. Your sulfur trioxide is absorbed by sulfuric acid. The heat is absorbed by water on the surroundings, just to keep it nice and safe. And then after that, your gas mixture is then passed for the final time through vanadium 5 oxide, and then you've successfully converted 99.5% of your gas mix, and you can then pass this through another run of sulfuric acid to turn it into oleum. Here is a picture of someone holding the vanadium 5 oxide catalyst. You can see it just exists as pellets, so it's quite an interesting picture there. So just to have a quick summary of all of the processes that take place. So you've actually got sulfur and air and water. Sulfur reacts with the oxygen in the air to form sulfur dioxide. It's very straightforward. 2s plus 2O2 gives you 2SO2. Please remember the state symbols as well. Then the sulfur dioxide reacts with more oxygen in the air to form sulfur trioxide. So you've actually got your reversible reaction. That's the one that you need to memorize. So you actually need to have more air. You've got your vanadium 5 oxide catalyst. You've got 4 beds of it, and you've got 450 degrees Celsius. The sulfur trioxide is then dissolved between the 3rd and the 4th bed in concentrated sulfuric acid. It's not dissolved in water. The reason why is because if you dissolved it in water, you'd actually get a massively hot mist of acid, which is massively dangerous. So you avoid that. By dissolving the sulfur trioxide in concentrated sulfuric acid, which around about 98.5%, you get 99% sulfuric acid, which is considered to be oleum. Some texts actually refer to the oleum as a combination of H2SO4 and SO3, so it becomes H2S2O7. but you're not expected to come up with that. The oleum, the hyperconcentrated sulfuric acid, is mixed carefully with water under controlled conditions. You get heat coming from it, and that heat is then used to turn more water around the coils into steam, and then that steam can be used to sell off electricity. So once you mix it carefully with water, you get the dissolved sulfur trioxide reacting with the water in a very straightforward reaction. H2O plus SO3 gives you H2SO4, and that is your concentrated sulfuric acid. So any extra volume of water that you've actually added to your oleum then turns into your concentrated sulfuric acid. You add water until you get back to your original concentration of sulfuric acid that you then run through to absorb more sulfur trioxide in this stage. So it kind of cycles that way. So the sulfur dioxide going to sulfur trioxide is a reversible reaction, and as soon as that trioxide is formed, the reaction goes in the reverse direction. So sulfur trioxide continuously breaks down to reform sulfur dioxide and trioxide. So it's not helpful. So to increase the chances of successful reactions, we use catalysts to try and get us to that point of equilibrium, and then we continually, after the third the third run through the vanadium 5 oxide, we remove the SO3 by dissolving it in concentrated sulfuric acid. Remember, the water coils are also always absorbing the heat to keep it safe and to also help with the economics as well. It is an exothermic reaction running forward, so you do need to bear in mind that you can't raise the temperature too high, but the catalyst, vanadium 5 oxide, will actually fail below the temperature of 400 degrees Celsius. So 450 degrees Celsius is a compromise. In terms of pressure that's used in the contact process, yes, increasing the pressure will increase the yield of sulfur trioxide. You've got 3 molecules on the left-hand side, and you've got 2 molecules on the right-hand side. So increasing the pressure will increase the yield, but in practice, you only really need a little extra pressure to less than 2 atmospheres for safety considerations and economics. So let's just quickly run through a quick quiz just to test that you've been alert on this one. What are the raw materials? Pause and play again if you once you think you know the answer. So the raw materials are sulfur, air, and water. What's the formula of sulfur dioxide? Pause. Okay, sulfur dioxide's formula is SO2. Sulfur trioxide formula. Pause. It is SO3. And what's the oily product with SO3 dissolved? Can you remember? Pause it. It is oleum, H2S2O7 sometimes it's called. What's the equation that, complete this equation to make sulfuric acid in the final step when you're watering down the concentrated sulfuric acid, the oleum? Pause it. Okay, it's H2O plus SO3. Now, these questions are more often than not, in your GCSE combined with questions to do with air quality and climate, which are slightly more simpler questions and straightforward questions. So just be aware of how these questions are actually structured. And if you need to, you can watch this video, which is on my channel as well. Everything you need to know about air quality and climate, that covers all of the features in the previous slide, including the gas desulfurization. All you need to do is just find it on the Year 9 playlists, I believe. Thank you very much for watching, and good luck in your exam. Let us know your feedback in the comments. If you think there's any improvement that can be made, please let us know, and also don't forget to like and subscribe. It supports the channel. Thank you very much. Bye.